Hello everyone, welcome to this session. My name is Wang Guanzhi. I work as a system analyst at Reuters. In this session, I will explore the application of container technology to the WRF model. Let's begin. Throughout human history, scientific advances rely on the spirit of open. Knowledge is accumulated, shared, practiced, and improved. This is a quote from Isaac Newton. If I have seen further, it is by standing on the shoulders of giants. OpenInfra is like the giants we all stand on. We at Reuters aspire to build solutions to serve the scientific communities based on open technologies. First of all, you may ask, what is a WRF model? The Weather Research and Forecasting Model, or WRF for short, is a regional mesoscale numerical weather prediction system designed for both atmospheric research and operational forecasting applications. The WRF model is jointly developed by National Center of Atmospheric Research and the National Oceanic and Atmospheric Administration and many other United States research institutes and government agencies, with frequent code contributions from its users. It is mostly written in Fortran, a dominant programming language in HPC application. I am a user of Fortran programming language too. It is open source, public domain software hosted at GitHub. It has large and vibrant user base worldwide, including our National Weather Service, Taiwan Central Weather Bureau. In all, the WRF model is a typical HPC workload in atmospheric sciences. Then you might wonder, how does the WRF model simulate the evolution of atmosphere? What is it actually doing behind the scenes? The WRF model simulates the evolution of atmosphere by solving a set of governing equations based on physics. The governing equations include momentum equations based on conservation of momentum, thermodynamic equation based on conservation of energy, continuity equation based on conservation of mass for dry air, moisture equation based on conservation of mass for water, equation of state based on ideal gas law. You can see the formula listed below for reference. On the left-hand side, you can see that there are terms related to time derivatives, or you can say the rate of change with respect to time. On the right-hand side, there are many forcing terms. They are determined by model physics, which are in turn controlled by nameless options. In other words, they are user configurable. Now look more closely at the formula. You begin to calculate every term in the governing equations, leaving only the terms related to time derivatives. Then you perform time integration on them and repeat. This way, you will know the evolution of atmosphere into the future. This is what the WRF model does. Now I will quickly go through the traditional method, also known as the bare metal method, to run the WRF model. This is what WRF model users or system engineers supporting such users typically have to do to get the WRF model up and running on their system. So here are the prerequisites. You have to set up HPC hardware and software environments. On the hardware side, these include compute, which CPU, memory, GPU, or custom accelerators do you need? Storage, you may want to consider parallel file system. Network, you may want to consider low latency, high bandwidth interconnects here. So next, you install the compilers of your choice. For the WRF model, at least C and Fortran compilers with support for recent language standards are required. Because you are doing parallel computing here, many compute nodes are involved. Your HPC applications likely need a standard way to do data exchange. Therefore, you have to install the corresponding MPI implementations for your compilers. The common ones include MPI-CH and OpenInfra. Then you have to install the necessary libraries for the WRF model. Here is a list of typical WRF model dependencies. You may recognize that some of them are common, while others are specifically used in scientific fields. You may also notice that some of them are denoted as optional, but if you don't provide them, some features of the WRF model will become disabled. Okay, so we begin to build the WRF model. When you attempt to build the WRF model, there are many things you have to be careful about, or the WRF model just won't build, like do not mix and match libraries compiled by different compilers, and you have to use the same compiler throughout the build process. And you have to set the correct values for some important environment variables during the build time. There are two standard steps in building the WRF model: configure and compile. During the configure step, you have to tell the build system about some important information of your computing environment. For example, what compiler toolchain are you going to use? Where are all the necessary libraries installed? Are there additional compiler or linker flag you want to pass? A WRF model simulation starts with static geographic data and global model data. There are many sources for these data. Most of them are from major operational NWP centers around the world. Some of them are available free of charge, while others are not, with certain restrictions. The first step is to run through the WRF preprocessing system, or WPS for short, as illustrated on this page. As the name suggests, it preprocesses various input data for later use by the WRF model. The WPS consists of several utility programs that perform different tasks, including model domain definition, data format conversion, horizontal interpolation of data, filling missing data, and more. A configuration file, also known as a namelist file, is needed to control the programs. Now we arrive at the core part of the WRF model. The real program performs vertical interpolation of data and is responsible for model initialization. It computes and generates boundary condition, initial condition, and analysis nudging data for each model domain. With everything ready, the WRF main program can finally start the atmospheric simulation. The results are stored into the WRF-out prefixed files. Similarly, a configuration file is also needed here to control the programs. So, up to now, you have seen an overview of how to run the WRF model. When you are in a position to actually do it from scratch, it is not hard to come to the following conclusions. The WRF model requires a highly specialized software stack where dependencies are often tightly interlocked. A single library can have multiple configurations. Sometimes only a specific one is supported. Take NetCDF library for example. The WRF model uses it for I/O-related operations. The NetCDF library supports serial and parallel I/O mode. However, the WRF model only supports serial mode. NetCDF library also have classic and enhanced data model support. The WRF model supports both. Then there can be multiple ways to integrate different libraries. Take NetCDF library for example again. For parallel I/O functionality, you can choose to integrate HDF5 or PNetCDF or both libraries. When combining certain versions of NetCDF and HDF5 libraries, data corruption bug occurs. All of this porting, tuning, and validation take time and effort. To make the matters worse, changes to the operating system, drivers, compiler toolchains, and libraries likely mandates a partial or full rebuild of the software stack, and eventually the model itself. Now think about it. If you have an HPC infrastructure, do your users use it for running a single specific workload? Or will you be facing mixed workloads from many different users? The latter scenario seems more likely. In this case, dependency hell problem arises when multiple different models or multiple different versions of the models of the same model have to coexist on the same system. We think containers may be helpful here. Although containers are seldom used in HPC workloads, we are going to try it. Next, we are exploring the WRF model. We are exploring to run the WRF model inside containers. Here is the schematic diagram of the WRF model container. The entire WRF model, along with its highly specialized software stack, are now packaged inside a container. Additionally, the modeling workflow are fully automated by the shell scripts inside. In this scenario, system engineers now just need to maintain a container runtime on the system. This should mean a much easier job for them. The status of the WRF model container can be monitored by mounting a status log file. Users are able to control the behaviors of the WRF model container by setting environment variables and by mounting custom configuration files. Users are also able to provide input data and collect output data by mounting directories or volumes into the container. This is a command line usage example when using Docker to run the WRF model container. You can see that we tell it to use 16 CPU cores for parallel computing. We tell it to do some tasks. By setting environment variables. We mount the directories for providing input data. We mount a configuration file to control the WRF model. We mount a status log file for status monitoring. We mount directories for collecting output data. This is a command line usage example when using Singularity to run the WRF model container. It is mostly the same as the Docker one. Singularity is a container runtime that is designed for HPC usage scenarios. So, we are going to run a simulation case with the WRF model container. The simulation case should be representative of the real-world usage scenarios of the WRF model. Here is the specifications of our test environment. For compiler toolchain, we use GCC 8 series. We use recent versions of the communication libraries, OpenInfra and UCX. We also use recent versions of Docker and Singularity. We first perform a benchmark run on our test environment to make sure everything is working in order. The LINPACK benchmark measures the floating point performance of a given system. It is one of the test items used to rank supercomputers for the top 500 list. The unit here is in gigaflops, floating point operations per second. Higher means better. Note that we only use 16 CPU cores on the system in order to reduce variability. The result of each run type is the average of 5 consecutive runs below. We find that there is virtually no performance difference between bare metal, Docker, and Singularity. there is little performance overhead in Docker and Singularity. For the WRF model configuration, we designed a model domain like the figure on the left. We use global model input from NSEP final analysis 0.25 degree resolution. Spatial resolution is from outer to inner 45, 15, 3 kilometers with 30 hybrid levels. The hybrid levels follow the power law scheme distribution. Simulation time spans from 2021 July 21st to July 25th, totaling 96 hours. There is a typhoon named Infra near Taiwan at that time. Some important model physics options are listed here for reference. First, we look at the performance results. This table shows the time needed for the WRF model to complete the simulation case. All model configuration and input data are the same for each run type. The unit is measured in wall time, hours, minutes, and seconds. Lower means better. For bare metal, it takes 7 hours and 3 minutes to complete. For Docker, it takes 7 hours 31 minutes to complete. This translates to a performance loss of about 6.5%. For Singularity, it takes 6 hours 40 minutes to complete. This translates to a performance gain of about 5.4%. By default, Docker drops many Linux capabilities in the container. This prevents the use of some system calls made by the OpenInfra to perform data exchange. As a result, other slower methods are used instead. So, Docker being slower is expected. However, it is interesting to see Singularity being the fastest by a decent margin. More detailed inspections are needed. Next, we look at some simulation results. They should be more interesting. These figures show the 3 hourly precipitation and the sea level pressure from domain 1, 2, and 3, from left to right. The time is at 2021, July 23rd, 12 UTC. The color bar is for precipitation. Unit is millimeters. You can clearly see that there is a typhoon here. It is the Infra typhoon. Although Infra typhoon did a right angle turn and did not make a landfall to Taiwan, it still brings significant precipitation to the northern Taiwan, as you can see on the figures. These figures show the surface temperature, surface wind, sea level pressure from domain 1, 2, and 3, from left to right. The time is at 2021 July 23rd, 12 UTC. The color bar is for surface temperature. Unit is degrees Celsius. you can see that the wind speed over the northeastern coastal areas of Taiwan can reach as high as 30 knots, as indicated by the backticks on the wind bars. Ships are warned to stay away during the time period. Containerization of HPC application brings many benefits: excellent maintainability and manageability for running a diverse set of models with multiple versions concurrently. Usage examples include ensemble simulations, modeling experiments, and you are able to add, remove, upgrade, downgrade models, or modify any part of the workflow just by swapping out the relevant containers. Containers offer consistent execution environment across different hosts. Therefore, excellent numerical reproducibility can be achieved. This is especially important for scientific usage scenarios. Portability across heterogeneous computing environment. For example, you can migrate to another host effortlessly without redoing any porting or validation work. When disasters strike, you can quickly move to another host and resume your work. System complexity is greatly reduced. Ease of use, faster and simpler training for beginners. In fact, we have developed a prototype of atmospheric modeling service. It recently graduated from internal proof of concept stage. In the future, this service will be integrated into the Garotas cloud platform. Through an easy-to-use web interface, users are able to run the WRF Model container or other similar workloads. Users are able to query the service status, configuration, request computing resources, provide custom configuration files and input data, monitor the progress and status, and finally, preview and download output data. For advanced users, this kind of users may demand absolute control over how the WRF model should be run. We also have them covered. We even provide terminal access into the WRF model container directly on the web interface. Here is our future work. We plan to support more modes of operation in the WRF model. Model restart run, one-way nested run, WRF data assimilation functionality. In the mid to long term, we plan to support more atmospheric models, model prediction across scales. LINPACK is one of them. So, thanks everyone for attending this session. Comments and questions are welcome.